Good afternoon. Let's start on time. Thank you for showing up on time, everyone. 45-minute session on segment routing, MPLS introduction. Follow the labels. So I'm Luc Degain, and I'm a technical leader in the CX department at Cisco, the TAC, more precisely. If you have questions, I prefer you ask them in Cisco WebEx app. After the session, I can't monitor while I'm here, and I'll try to answer them as soon as possible. If you really have something burning, we can probably squeeze in 1 or 2 questions now. Otherwise, let's stay after this one, after the 45 minutes after the session, and let's stick around, and I'll try to answer the questions then as well. All right? The WebEx app is open until June the 17th. So this is the agenda. We start off with a quick introduction. We'll talk about the labels and the MPLS forwarding. Small section on TI-LFA, the protection, but actually a really important one, I would think. And then 2 bullet points there, a little bit more advanced, which is the SR policy, or the traffic engineering, with segment routing and on-demand next hop. And we'll round it up with some OAM, operation, administration, and maintenance. So first of all, if you want to stay up to date, here are some links. Obviously, you can also go to www.cisco.com, and you will see what appears there regularly. This session is on SR MPLS, not the SRv6. We don't cover that at all. So it's all about labels and nothing else. The services that you know in the upper layer, right, the overlay, IPv4, IPv6 transport, VPN v4, VPN v6, EVPN, VPLS, point-to-point, pseudo-wire, whatever, that will still work with segment routing, right? That worked before. Doesn't matter what you have in the underlay, LDP or something else, or segment routing, that will still work. And anything with inter-AS, option B and C, if you know that, that will still work as well. No change there. So why, years ago, did we invent segment routing, right? Well, one of the driving factors was simplification. Getting rid of a protocol like LDP is simplification. LDP was fine, not perfect. It had its little quirks now and then, but it was kind of fine. But getting rid of a protocol, that's definitely better. One thing, if you're, especially in a migrating phase, if you're migrating from LDP to segment routing, for example, there is still interworking. So the forwarding will still work from SR to LDP or the other way around. No problem there. Second bullet, probably even more important, is no classic traffic engineering. Traffic engineering based on RSVP, right? Very difficult to implement, difficult to maintain, and even more difficult to troubleshoot. And not very scalable either. Thirdly, load balancing by default. Looks kind of silly, but if you think about the classic traffic engineering, that's something that never happened. Your traffic engineering tunnel always took one path, and that was it. Never load balancing. With segment routing, always load balancing. Simplified forwarding. Again, if we think about what we were doing with classic TE, the RSVP-based TE, we had lots of options, and one was more complicated than the other. We had auto-route announce or auto-route destination, static routes, and so on. Many options, always a little bit quirky. With segment routing, the steering is automatic. That means when you get something that demands forwarding, which is typically a service route, a VPN v4 route, or something EVPN, we will install the forwarding. That's it. You don't have to even configure something extra. Better protection, I think that's a very important one. Even if you just deploy the basic segment routing, which means MPLS forwarding, and that's it, the pure basic underlay, you get the advantage of TI-LFA. So very good protection, and always, all the links and nodes are protected. More about that later. And finally, also very important, many new features that didn't exist before in the MPLS world or the classic traffic engineering world, right? To name a few, path disjointures, so multiplane routing, the 2 paths are always not touching each other. Microloop avoidance when we are doing protection. Very important, flex ALCO, so dual plane routing, if you want to call it that. Oh, and multicast, my favorite topic. We now have multicast integrated with segment routing as well. We call it 3-SID. 3 because it's segment route, because it's multicast, and SID because it's segment routing. Right? That is working now as well. So in a nutshell, what do we have? First of all, segment routing is source routing. It's all about the head-end router. The head-end router will instruct how the packets are forwarded. It does that in our MPLS world by creating a stack of labels. And each label will represent a segment, a path, in a part of the path in the network, right? So in the data plane, as I mentioned before, we either have MPLS for the forwarding or SRv6. SRv6 is the normal IPv6 forwarding plus potentially one additional header to make it all work. And there, basically, one IPv6 address signifies one segment or a part of it. If you heard about microSID, you know what I'm talking about. But we're going to look at MPLS labels. Normally, we always take the shortest path through a network. Traffic engineering, source routing means we're going to deviate from that. How to do that? The source router will create, in our case with MPLS, a label stack where each MPLS label signifies a segment, a little part of the path to follow. Right? And you could do the same with IPv6 as well. We have the control plane. Very importantly, the control plane for segment routing must be a routing protocol. Why? Because we are doing traffic engineering. Any router in the network can be a head-end router and needs to know the full topology. So we need link state routing. EIGRP will not cut it. But we can call in the help from an SDN controller, a controller, if we want to. You don't need to, but it's possible. We can do that. And that can be programmed in different ways, or it can suck up the topology in different ways, but BGP, PSAP, and so on. Path options, if you're familiar with classic traffic engineering, you know what this is. You have two options. It can be either done dynamically. That means that the path computation is done on the route itself. It has a topology, at least within one area in OSPF or the level in ISIS, so it can calculate a path, or explicitly. Again, that's kind of the same thing as what we were doing in classic traffic engineering. All right. Let's talk about the labels, the MPLS labels. I mentioned it. We have segments, segment routing, right? We have a path. We chop it up in segments, 2, 3, 4, whatever. Each of these segments, little parts, will be identified by one MPLS label. So that's pretty straightforward. We don't have LDP anymore. So who's advertising the labels? It will be the link state routing protocol. So they were enhanced many years ago, extended, so they can advertise their labels. We kind of have two kinds of labels, and that's very important that you know what they are. On the one hand, we have what we call the prefix SID labels. So SID is segment identifier. In our case, it will always be an MPLS label. The prefix SID label is kind of a node label. It identifies a node, so a router. More on that later. An adjacency SID, the word says it, adjacency, it is from one router to the next hop router. It actually identifies just a link, right? So two kinds of labels, keep that in mind. So we are getting rid of LDP and RSA-PTE, and a controller is possible if and when it is needed. So let's have a look how the forwarding works in the SR world with MPLS labels. So you have the overlay, whatever service is it, L3 VPN, EVPN these days is very popular. It really doesn't matter what you have there. In the underlay, you will have MPLS forwarding driven by segment routing and the link state protocol. Here's an example of a prefix SID label, a node label. P3 would advertise a node label for itself. But what it actually advertises is a prefix SID, and that's just a number. It's an indexed number. Keep that in mind. But it will relate to a particular label. And other routers, for example, PE2, will do that in the same way. One label for that router, and it's tied to the loopback. We also have the adjacency SID labels. This is a label which is tied to a link. So, for example, from P3's perspective out towards P6, there is a label. Another link will be another label, right? And all the routers do this, obviously. So now when we want to forward packets from P1 to P2, and let's say we want to do it over this path, then we can possibly carve it up in 3 segments, really making sure that the packet goes over this middle vertical link. And we do that by its source routing. The head-end router, P1, sending out the packet with 3 labels, 3 segments, from top to bottom, first to last. Top label is the label which is a prefix SID label, so a node label. This is just a label that gets the packet towards P3 or beyond, but via P3. Note that at every end of a segment we have penultimate hop popping, so we actually pop off the top label. So the packet arrives at P3 with this label, and this label is actually the adjacency SID label here. P3 knows packet should be forwarded out on this link, and it forwards it out. Again, penultimate hop popping by P3. The packet arrives at P6 with the last label 16007, which gets the packet to P2. Okay. The head-end router does source routing. We have a label stack. In the label stack, potentially a mix of prefix SID, node labels, and adjacency labels. Okay? Node labels get the packet to the router, no matter how, which path, usually the shortest path. And the adjacency SID label means that label means forward the packet on a particular link from that router. How do we get that to work? Well, you need a link state routing protocol, all right? That's the first thing. We need 2 kinds of label, the node labels and the adjacency SID labels. The node labels will be taken from a particular range, by default 16,000 to 24,000 minus 1. You can change that. Routers can have different sRGB, segment routing global blocks, but it's probably better if you do the same range everywhere. So that's important. The prefix SID labels, the node labels. Second is a bunch of adjacency SID labels. How many? Well, as many as links on the router. Could be 5, could be 1,000. It's probably a lot, but it's possible. So that's what every SR-enabled router advertises, either in OSPF or in ISIS. Now, the node labels obviously need to be globally unique because it identifies a node, a router. The adjacency SID labels are not. They are unique inside a router only. They're tied to one interface. So that's why these labels, the adjacency SID labels, are taken from the dynamic label range, meaning starting at 24,000 up to 1 million something something, right? 24 bits. So these global labels or prefix labels or node labels just get a packet from a particular router, in this case P1 to P6, by using the label, the node label of P6. But if you look at it, this could be a possible path. If every link in this network has the same metric or cost, then in total we have 4 paths for the forwarding. Right? So by default, 4 paths, here in this case, 4 paths for ECMP, equal cost load balancing. And at every router, we use the same label. That's kind of easy to follow, easy when you're doing troubleshooting, and so on. And we need only one label to get the packet from one end to the other end through the network. Those are the node labels, prefix SID labels. The adjacency SID labels are tied to a link. So any router will assign an adjacency SID label, an MPLS label, from the dynamic label range, so 24,000 and above, to a link. So for example, P4 will assign 24,003 to link 3. That means if a packet does arrive at P4, due to using the prefix or node label of P4. Here we have penultimate hop popping. So the packet arrives at P4 with top label 24003. This packet will be forced to be forwarded over link 3, right? Not any path anymore, but this link, that's it. So it ties the forwarding to a link. Like this. All right. So that's the basic SR MPLS forwarding. I don't think it's that difficult, right? Important note, what changes in the MPLS forwarding? Absolutely nothing. So all the things that you know about MPLS forwarding with LDP or I3PT stay the same. So we have the special labels 0 to 15. For example, label 0 is explicit null. We still have that with segment routing. Label 3 is implicit null, penultimate hop popping. We still have that with segment routing. 20 bits for the label range. We have the TTL propagation. We still have that with segment routing. We have the experimental bits, or the traffic class bits, and how to use them with the 8 levels of quality of service. The same thing with segment routing, and so on and so on. So there's no difference here in the data plate. Obviously, this is very useful because that means if you bought hardware, if you're forwarding MPLS packets that got there by LDP or segment routing, it's the same hardware. You don't need to upgrade ASICs just to get segment routing support. Three operations that we've always had in MPLS are push, swap, and pop. Well, we have them with segment routing as well. So on the Ingress router, when we get an IP packet or a layer 2 packet, if it's EVPN, for example, and we need to push a label, so do label imposition, one or more labels, you will see in the routing table, and usually I give the example of iOS XR, you will see that this route is actually marked as a labeled SR route. And if you look in the FIP table or the CEF table, you will see that we start imposing one or more labels. So if that payload comes in, it will receive that label which is governed by the FIP table. That's just label imposition. Same as before. Label swap, when you look at an intermediate router, packets come in already labeled, one or more MPLS labels in the label stack. That means we don't do an IP lookup or an L2VPN lookup, but we look it up in the LFIP, the label forwarding instance space, right? So the command you would do is show MPLS forwarding on all our operating systems. And you will see that the packet there, so you have an incoming label and an outgoing label. Outgoing interface, outgoing IP address, this is the same as always, just now that you will see that the prefix will be marked and it says SR prefix, so it's a prefix SIT. Index 4, so the label is 60,000 plus 4. Forgot to mention, but the way we advertise the labels, no matter how you configure it, but the way we advertise those global labels, the prefix SIT labels, is always with an index, so meaning it will be the start of the segment routing global block, 16,000, plus the index. So just label swapping, and again, usually we don't change the label, right? Incoming label is the same as the outgoing label. Pop label, same as before. Packet comes in, we look at the LFIP. Packet comes in with a particular label, goes out with a label less. Pop means remove exactly one label. Same as before. Now, maybe one difference, we are most of the time used to popping labels at the egress router or at the point of local repair when you're doing protection. Now, penultimate hop popping, usually happens at the end of a segment. Right? So, as we've seen before. So, packet comes in on R3 with 2 labels. It's the penultimate hop router of the segment. It pops one label and forwards it with the remaining label in the label stack. The LFIP, so if you look in the forwarding table for incoming labeled packets, show MPLS forwarding, you see what we are used to before, incoming and outgoing labels, outgoing interface, and so on. you see pop, implicit null, explicit null. Here you will see either SR prefix, for example, which is the prefix SID labels, node labels, or the adjacency labels, the local ones, the ones tied to the links. And maybe some other exotic stuff, usually which is tied to the forwarding related to what we will see, SR policy, ODN, and things like that. We still have the load balancing there, so one incoming label and you have two outgoing labels, the same or different, but pointing out to two different outgoing interfaces. So here we are doing a load balancing, right? Anybody has a question? All clear? All right. Protection. In my humble opinion, one of the most important reasons to do segment routing. The protection with segment routing is TI-LFA, right? We've had LFA a long time before. In fact, I did my first presentation on that 10 years ago, I think. It worked in the IP world. We also call it fast reroute or IP fast reroute. And it worked in the MPLS world, specifically with LDP. And we actually used LDP there. If you remember remote LFA, it used remote LDP sessions. The good thing about it, it's all local to a router. All the computation is local to a router. There's no extra protocol. There's no extra signaling. And you can get link or node protection with it. Right? That was LFA. It kind of worked fine if it worked, if it was possible. Sometimes it was not possible. If you had a very complex topology, you didn't get protection at all. It's all or nothing, right? 0 or 1. What is a complex topology? A topology where it's only very sparsely partially meshed, if you know what I mean. Not fully meshed. And or the metric on the links are quite different. You have a part of the network where the links have a cost of 10 and 20 and so on, and another part where they're 10,000, 11,000 and so on. There's a big difference that will prevent protection in some cases. Or the worst case, when you have a link with different metrics on both sides. On one side a metric 10 and on the other side 10,000. Well, you won't get protection with LFA. Comes in TI-LFA, the name says it, topology independent LFA, you will always have protection. And again, the reason is because of the way SR works. The head-end router, or the point of local repair, the guy that sees his link going down needs to divert the traffic. He can suddenly just push 2, 3, 4 extra labels, as many as needed, to make sure the packet goes on the backup path in a safe way. Safe meaning it doesn't backflow, it doesn't flow back to the sender himself. Why is that important? Well, then you get a routing loop temporarily, but nevertheless a routing loop. So the pushing of the extra labels makes that TI-LFA is very safe. It's also topology independent because, remember, for segment routing, you need to have a link state routing protocol. So every router runs the link state routing protocol and it has the link state database, so it knows the full topology. So it knows, by looking at its database, how to forward the traffic over a backup path in a safe way. It has all the information there, right? Before, we did not say, with LFA, you need to do link state protocol. We did not enforce that. So, with TI-LFA, you can still protect IP and MPLS traffic. It's very similar in many ways to the old LFA implementation, like the tiebreakers, if you know what it is. Similar algorithms, similar ways to configure it, similar way to do the show commands, etc., etc. So it feels very similar as an operator, but inside it's completely different, right? All right. Anyway, what do you need to remember? No signaling, I mentioned it. 100% coverage, I mentioned it. Thirdly, when we switch from the protected link, or link to a node, which goes down to the backup path, with LFA we could switch, And then when normal convergence happens, so a few seconds later the routing protocols run their SPF, we switch again, sometimes. So potentially it switches 2 times the traffic. You will always lose a little bit of traffic. With TILFA, the protection goes from the link you are protecting, the protected path, immediately to the post-convergence path, right? Because, so if the link goes down, we switch the traffic in under 50 milliseconds. Then a few seconds later, OSPF ISRS runs SPF, finds a better path. Fine, but the traffic on the backup path is already on that path, the post-convergence path. So the best path after the regular convergence. Let me give you an example. So TILFA, source destination, we're trying to get traffic from the source to the destination. Obviously this is the best path and this is the label we are pushing. Pretty obvious. In the old world, it's not that long ago, with LFA, the backup path would be like this, because it's only one hop. Fine, when the traffic gets deviated to here, if this link goes down, R5 will forward it onwards. There's no risk of backflowing the traffic. Fine. But then, a few seconds later, R1 starts doing SPF and ISIS or SPF and finds out that this is now the new best path, because this has an overall cost of 30 and this is 200. So a few seconds later, the traffic switches to this path. So we have an extra switch. Sometimes, depends on the topology. With TILFA, when this link goes down, R1 will force the traffic to go over this path. It will use a label to make sure the traffic goes to R4, for example, and then onwards. And then a few seconds later on R1, when it does its calculation, the traffic is already on the backup path. How to check all this? Well, the same way as we checked it with LFA. And again, I give you the example of iOS XR. A routing entry, we see a protected link and a backup path. In ISIS, you see that you go to what we call a P node, a repair node in this network. So when you look at R3, this is the link we are protecting. The backup path goes to R6. R6 is far enough so that if we force traffic to go to R6, it doesn't come back, no backflow. So router 6 is the P node, and we use its label on the backup path. And in the FIP, CEF table, we see again router 6 as the repair node with its associated label. We call this the single segment example. When the protection occurs, we need to push a single segment. We need to push one additional label, right? You have also zero segment example, no extra pushing, or 2. We push 2 extra segments. If you're still awake, you see that we push 2 labels, by accident. In this example, this is the case. But this is the case because R5 is directly connected to R3. So when you forward packets R3 to R5, we have penultimate hop popping. So you start already with 0 labels. Usually it should have been 1 if R5 is a couple of hops away. So, yeah. But it's pushing 1 extra label. SR policy. So let's leave behind the basic SR stuff, the basic forwarding, and the protection. And let's go to a little bit more advanced stuff. We could call it traffic engineering if you want to. SR policy. So what is an SR policy? It's getting rid of the old, that's one thing, getting rid of the old classic traffic engineering, RCPTE based, and doing it in a new way with SR policy. So we're still going to do traffic engineering, right? Steering the traffic over a particular path, and we still want to attract traffic and forward the traffic over the SR policy instead of the old T tunnel. So we do steering of traffic. It's segment routing. We know that we no longer have core state in the core of the network, right? This used to be RCPTE signaling, a lot of it, not very scalable. Now we kind of put the state in the label stack of the packet. Right? All the segments are in the label stack of the packet. We can do dynamic explicit, I mentioned this already, and we can have the possibility of a PCE, path computation element, which is the controller. Right? It can talk to PCCs, path computation clients, routers, and yeah, do the path calculation in behalf of the router. What is a path, an SR policy, sorry? Definition of an SR policy, and this is kind of important. We always look at a head end. Head end is important because we do source routing. What do we look for? Where do we send the traffic? So there's an endpoint, usually the egress PE router. And for whom? For which prefixes? Which service prefixes? VPN-v4, EVPN prefixes, whatever. How do we identify those prefixes for whom we do SR policy? Well, we're going to look at the color. So those routes need to be colored. We will see in a minute what that is. And that's basically it. That's what an SR policy is. That's something you can configure only on the head-end router. There's no tunnel with a tunnel end, tail end, where you configure something on the tail end router as well. So in SR policy, we have different candidate paths. If you're familiar with traffic engineering, you know what that means. We had that for a TE tunnel interface as well, traffic engineering. You have multiple possibilities to calculate the path. A dynamic, another dynamic, an explicit, another explicit. One of them will win, and one of them will determine what the path of that tunnel is. We have the same with SR policies, multiple, we call them candidate paths, with different possibilities. One of them will win. If all of them potentially deliver a valid path and are valid, then the one with the highest number will win, the preference. Different attributes, for example, the type could be an IGP or a TE metric, like we had with classic TE, but now we also have hop count or latency. Right? And other things which I will not go into depth, but some of them come actually from the classic TE world as well. Okay. This is just some examples I took to illustrate. So under segment routing, we have different ways to configure a policy. But what is important, not the details, it is that the policy always has a color and an endpoint. So where to go to, the egress point, and the color for which prefixes. And then different candidate paths with different preferences. One could be dynamic or explicit, and you can have as many as you want to, with different characteristics each time. This is an example of an explicit one. You can either define it by segments, and the segments are defined by an MPLS label or an IP address, and you can mix and match. If you see PSEP, it means we use the PCE protocol. It means that the router will delegate a part of its work to a controller. A controller could be our iOS XR router. It can serve as a controller as well, be it a virtual or a real router. For example, it can delegate the path computation part to the controller. The controller will come back and say, this is the path you use. And then the router will use that path. And one more thing I will talk about is the binding SID in a minute. Right now. What is a binding SID? That's also important because you might end up using it from time to time. A binding SID is actually a label that is uniquely tied into the SR policy. Every SR policy will have one binding SID, one, you could call it an incoming label. It's done and assigned automatically, but you can override one and configure one statically, like there we have the binding SID label 1000. What is it used for? An SR policy is easy to use when you have IP traffic coming into it. The FIP steers automatically the traffic onto the SR policy by looking at the color. The color is some numerical value. But if the traffic is coming in labeled, that's not always that easy. If the traffic comes in labeled, well, we will somehow need to make sure that the traffic comes in with label 1000 in this case, and then that traffic will be further label forwarded onto that SR policy. Right? So 2 examples. What if you have 2 policies in your OSPF network, one for area 1 and one for area 2? And you want to make sure the traffic goes over SR policy 1 and then SR policy 2. Well, instead of using all the labels here and potentially configuring 6 labels, in the first SR policy, you could configure it with 2 segments, and then finally the binding SID label. That means when the packet arrives here on the area border router with label 25,000, we'll say, that router will say, that's my binding SID, it's tied to this SR policy, I remove that label and I replace it with the following 3 labels. So to get it to area 2. Another example, and this might be a little bit counterintuitive, you could use it when you go from a classic traffic engineering tunnel to SR policy, but also the other way around, which is what I did here. So from SR to classic TE. We assign to the classic TE tunnel 1000, whatever, a binding SID label. Then if the traffic comes in with that binding SID label, so it came in over an SR policy, it will be forwarded out on that particular classic TE tunnel that we have there. So think of it, you know, daisy chaining of SR policies or other kinds of tunnels. Automated steering. What is important is that color you configured here and the endpoint, and then it can automatically attract traffic. So it's per destination steering. Traffic going to that egress router, to that endpoint, with the color, whatever, 100 assigned to it, will be forwarded over that SR policy. So then it will get the label stack, which is tied to that SR policy. Obviously, with show commands, you can figure out what the label stack is, but I'm not showing that here. Or, if you really want to, you can actually use static routing. You can point a static route to the SR policy. The only thing is, you have to specify the SR policy with a color and an end hop, so in a specific syntax. Again, if you do show commands, it will give you that syntax easily. Something newer, it's not just per destination steering, get the traffic to the endpoint, but it can also be cost aware. So we have a main SR policy, and then some kind of per flow SR policies. I configured 2 of them here, color 100, 101. And each of those colors can take care of a subset of quality of service. One can take care of the quality of service 0, 1, and 1, and the other one, all the rest, and so on. You can have up to 8 levels. Right? So per cost or per flow steering is possible as well. On-demand next hop, it's kind of exactly what we have just seen. An SR policy forwarding traffic, which is for colored service routes. But this time, you don't need to specify the next hop. On the SR policy, you just put on demand, and the SR policy will be created whenever it's needed, meaning whenever it gets a service route, it will create the SR policy. We don't care anymore about the next hop. So where does the next hop come from? If you don't configure it as an endpoint, it will be the BGP next hop. We're always kind of using BGP, right, for the service routes, IPv4, VPN, EVPN, and so on. It's always BGP. I just gave you an example. Let's say, and that's a really good example. Years ago, people would have configured unified or seamless MPLS here. Why? Because you have different areas. You don't want to distribute the loopback of all the PEs in one area into the other, ISIS or SPF, right? So what you did, you transported them with BGP. Which kind? BGP labeled unicast, so the BGP route, the loopback of the PEs, plus a label. And that kind of scheme we call BGP-LU or RFC 3107. Very popular model. Well, this can now be replaced with SR policy and more specifically ODN. Actually, I will show on the next slide. So this is the same network. When a prefix comes in on a PE router, it will be colored. Now that is something that you will need to configure. It's a BGP extended attribute that you have to tie in, but it's just a number. So you make sure those prefixes coming in receive a color or are assigned to an extended community. It's just a number. When it goes to the ingress router, so here we have an SR policy configured, matching that color but we don't specify the next hop PE2. We don't need to, because when the BGP prefix comes in, we see that the next hop is PE2. So we first match the next hop in BGP route and the color. Then we create the SR policy. So not when you configure it, but now it gets created on the router. And then finally, we install in the FIP table the route with all the outgoing information. Most importantly, the outgoing label stack. Quick word on the controller. A controller can be there. It can be anything. We have an XR router, which does the job perfectly. The controller is there to oversee the whole network. Let's say you have a segmented network, or you have a network with multiple areas or multiple ASs. Then one router doesn't see the topology everywhere. Link state routing stops at the border routers, right? So controller will get that complete topology of the whole network, either directly via ISIS or OSPF, or via BGP with BGP link state address family. So it knows the complete topology. For redundancy, you can have 2 or more controllers, but I only show 1. Now, if the head-end router doesn't see the complete topology of the network, it can't compute the path, the SR policy and so on, won't work. What it can do, it can delegate the path computation to the controller who knows the whole network and says, give me a path. The controller calculates the path and returns what we call the explicit route object. So it's a bit the same as with classical TE. It's the number of segments to follow, but now the segments are not IP addresses, there will be an ordered list of MPLS labels. All right. Eventually, the SR policy gets installed, it comes up, and all the prefixes, the service routes, will be installed in the FIP table, and traffic can start to forward. Any questions on controller? All right. I'm almost done. Maybe you can aim for 1 question. All right. SR operations, administration, and maintenance. What a big word for a little thing. This is only useful for troubleshooting, right? Well, except some smaller corner cases, but it's really, really there for troubleshooting. We have had this a while in the MPLS world. Why? If you just do ping on traceroute, what do you get as feedback from the output? It works or it doesn't work. With traceroute, okay, it might stop at a certain router. But in the MPLS world, it's really it works or it doesn't work, because when you do a traceroute, the packets always go to the remote end and then back. So you don't get a lot of information. It works or it doesn't work. Binary. With MPLS OEM, which existed before, even with LDP and so on, you get a lot more information. There's a lot more verification happening, specifically with traceroute. At every intermediate router, we don't just check if it works and we get, the message back saying that it worked. We verify if the label is correct. We verify if there is a label, if the label comes from the right protocol, and things like that. So really a lot more information. And we even did that for multicast. Now the point is, we also are doing it specifically for SR MPLS, but it's kind of 3-4 things. You can do with a generic FEC type. FEC, do you know what that is? That's the forwarding equivalent class. It kind of says what the service is. Is it for LDP, segment routing, pseudo wires, whatever. We just say FEC generic, so we don't care. It's just a generic test. So we get a little bit less information. We check a little bit less, but still, it's really good. This one is the newer one, ping SR MPLS FEC type IGP, ISIS OSPF. It will just, at intermediate routers, check for SR if it's really the right prefix sits in ISIS or OSPF that we are using, and so on. So it's a specific ISIS OSPF check. Very good is the traceroute SR policy, because policy, think of it, traffic engineer path end to end. So this one, when you do a traceroute, it's a traceroute inside the policy, so the traffic engineer path. We kind of had this before when doing traceroute in a pseudo wire or yeah, whatever else, tunnel, traffic engineering tunnel. NILFEC, last thing, this is really good. It's kind of also, yeah, there's no FEC, we don't check the FEC specifically, but here you can really force the path of the traffic. So let's say you have this network. Obviously, when you do ping traceroute, no matter what, it will always take the top path, the shortest path. Here, how could you check the bottom path? Because this path is not, you know, on the shortest path because this link is so high. How could you check that? You could verify it by doing a traceroute with 3 segments. Segment 1, segment 2, segment 3, right? And force the traffic to go over this link with a high metric. You can do that by just doing traceroute, MPLS, NILFEC, specifying all the labels of the label stack and the outgoing interface. So you force the traffic to go over a non-shortest path. So you could check all your paths if you want to. You have a lot of time in your network, right? All your LSPs, label switch paths, you can now check. Key takeaways, it's simpler, it's easier to troubleshoot. Protection, don't forget the protection, really nice. And then a little bit more advanced stuff are the SR policies for the traffic engineering, if you choose to do that. You don't have to do traffic engineering, right? That's not a must. Don't forget the survey, and these slides which you have already seen. So, if you still have questions, just come to me after the session. I have plenty of time. I hope you do as well. And we can have a chat. Otherwise, thank you for being here.